Okay, in the last video we talked about a machine that would create universal infinite graph paper. Now we need to try to invent a geometry or a mathematics that would operate that machine or create that machine. I mean, it required the existence of these two perfect solids. The problem is that we can't assume that they exist. That's a homunculus. We can't just say, oh, there you go, voila, you've got these two things, now start using them. We need to imagine a universe in which these things come into existence. And so that's what geometry is. We can't use these to build geometry. These have to be built from geometry. Okay, otherwise it's just a homunculus. Now, what you need to know is that all math is a contrivance. It's artificial. It's a man-made. We contrive math so that we can use it to describe stuff. So, for instance, we want to describe that. That's gravity. All right, nobody invented gravity. We don't need to explain what it is. We all know what it is. The damn thing pulls stuff to the ground. You know, in the old days, they used to just tell stories about it. That's what Aristotle did. And for hundreds of years, that's all anybody ever did, thousands of years. And that's all they could do. But, you know, Newton came along and says, no, we can describe gravity mathematically. So he did that. He invented the mathematics of gravity. And that's what we mean when we say gravity. So he had this contrivance, this mathematics, this absolute time and space that had these coordinates. And it was based on the idea of a cube and Cartesian coordinates, which is what they are, is cubes. And then he said, here's mathematically what gravity is. Well, Einstein came along and says, well, that's close, but not quite. Really what it is spherical. It's non-Euclidean. All right, so he created a new contrivance. Well, he didn't create it. Riemann created it. And they have this new contrivance that's spherical, non-Euclidean geometry, and it describes gravity. Okay, he didn't invent gravity, he invented the mathematical contrivance to describe it. And it's non-Euclidean. And on the bottom end of things, quantum mechanics, they don't invent they don't invent atoms, they invent a mathematical description that creates atoms. And here again, it's mathematical and it's non-Euclidean. So we know that they're both based on fields and they're non-Euclidean fields. And we know that life has to share features of both. It's bigger than atoms, it's smaller than gravity. And so it must be a field and it must be a non-Euclidean field. So that's just dead nuts simple logic. So we need to come up with a non-Euclidean mathematics that explains life. And in fact, the way we're going to do it is we're going to ask life, well, what are you doing? Okay, instead of us inventing a math that say, here, do this, let's say, what are you doing? And then invent a math that's consistent with that. So I explained this to my wife. I'll explain this non-Euclidean geometry. I call it pheometry, and I'll explain why. But anyway, the math that comes out of it, my wife says that's biomath. That's exactly what it is biomath. So we're going to invent pheometry to explain biomath. Well, you need to know that all geometry, all math is based on postulates. Well, a postulate is just a contrivance. We have to contrive a truth that we can't prove. Kurt Gödel proved that we have to do that. So all math is based on geometry. All geometry is based on contrivance. So Euclid had these 5 postulates, 5 contrivances, and they said, oh, that 5th one's not true. And so that's how they went from cubes to spheres. Unfortunately, that's not true either, because he has all these other postulates that he doesn't even state because they're so obvious. I mean, he says that, well, of course, we're going to build order with our geometry. That's the whole point. We're going to build order, and then we'll build order with order. Well, that's a postulate. That's a contrivance. You know, that's ancient thinking. We know now that if the universe is ordered, it's only because the order is emerging out of chaos. The universe is actually chaotic. Atoms are chaotic. Okay, the atoms generate, when they go from gas to liquid to solid, they generate the order. The order emerges from the atoms. You know, the graph paper doesn't tell the atoms what to do because the atoms can't see graph paper. The atoms are creating the graph paper. They're showing us when it makes great. When it makes salt, when the atoms make salt, they're showing us the answer. The answer is cube. The question is not cube. We don't say, how do you make salt out of cubes? The answer is cube. Okay, so we got cause and effect. The atoms are showing us the graph paper. We are not showing them where they can go. They're showing us, they're calculating that. So we need to reverse this cause and effect. Instead of trying to start with order, let's start with chaos and then find out what kind of order will emerge out of it. Now the other postulate is that we're going to go point, line, plane, volume, which implicitly means that space is three-dimensional. Well, that's just goofy. Space is not three-dimensional. That's just a contrivance. That's a simplification for the purposes of notation. I mean, we can experience the fact that there are infinite dimensions in space. I mean, we can just create, when we point, there's a dimension, there's a dimension. There are dimensions all over the place. So if we're going to use 3, it's because we break infinity down to 3. It's not that we build infinity from 3. So my point is, if you're going to go Euclidean, go Euclidean. That's what they did with this stupid ass table. That's pure Euclidean dumbass thinking. Okay, if you're going to go non-Euclidean, don't be a pussy about it. Go non-Euclidean. I mean, you know you're going to end up with spheres. Why not start with spheres? Say that that's the fundamental unit of space. It's a volume. We're going to take volumes, chaotic volumes, and break down to ordered points and lines and that kind of stuff. It's not nearly as hard as you would think. It's actually easier because there's fewer parts. So let's jump into that and see how it works. Well, the way that Euclidean geometry works is we build these lines, planes, volumes, and the simplest one is a cube. Well, we've used lines, planes, and volumes to build this, but we use just spheres to build this. We say, well, they're the same thing. Well, no, they're not. This thing is spherical and this thing is not. So if we imagine that this is the fundamental unit cell of Cartesian coordinates, we can say these are Cartesian coordinates. Well, if these were atoms making this, the atoms don't see these coordinates. All they can do is see from the inside out. So each atom in these coordinates sees the same thing. It can only see where it touches its neighbors, okay? So if you go inside that and you go to the point at the center of it and you look out, you see a surface with 6 points. Okay, that's how the Cartesian coordinates are generated. So now we just generate an infinite field of these spheres. Those are our coordinates, and then we set about naming them. And we start 1, 2, 3. Those are our digits. Those are our counting numbers. They're all the same, okay? And they all end up creating this language, this cubic language, that we use for our mathematics. And to most people, most normal people, that's what math is. It's this language of these coordinates, okay? But the universe isn't like that. For instance, we can fill the entire universe with infinite cubes and make cubic coordinates, but within that infinite field of cubes, you'll never generate a single dodecahedron. Well, to me, that's disqualifying. That means this is wrong. You can't do that. Because we know we have one of these. You got to have one. So you can't go from this to this, but you can go from this to this. Look, we just did. We took this. We made 5 of these. Okay. So our coordinates at the very least must start here and go here. Okay. We're going to start big and go little. We're not going to start little and go big. Okay. We're going to figure out how we can make one of these. And then we'll figure out how we can make everything else. Well, it's not that hard to do. We can do it remarkably simple. In fact, we can make all 5 of these at once with just 2 lines. I mean, how much information do you need? How much spatial information do you need to generate these 5 perfect solids? How many lines do you need? How many angles do you need? How do you position these things? The answer, remarkably enough, is you just need 2 lines. You can start with 2 lines and generate all 5 perfect solids. Well, that's unreal. I mean, that seems impossible, but it's not only possible, I'm going to show you how to do it. So if we start with a sphere and we say that's 1, if we take another sphere and we say that's 2, and these spheres are all the same size, then we can go on and create these Cartesian coordinates. But if we do it that way, we end up with a very limited and contrived mathematics that doesn't work for what we need it to do. So if we say that this is a sphere, and we know logically that it has a point in the middle of it, then a sphere creates a point. Okay, now if we say this second sphere comes in and touches the first sphere, then the 2 spheres create a line, and they also create a metric of scale. It says that this line is equal to this line, and there's no angle, because no matter how we rotate the one sphere on the other sphere, we're going to have the same angle between those 2 lines. So now if we come up with another sphere that's smaller and we put it here, now we've created a straight line between these 2, but we've also created an angle, because this sphere can now rotate, and then they can all 3 touch. So when that happens, we create a mechanism to generate angles. So if it's over here, then it's 180 degrees. If it's over here, it's something less than 180 degrees. This sphere here doesn't know what's going on outside of it. It has no way to know. All it knows is the lines and the angles that are created as a result of the contact with these other spheres. So now, the only thing we have left to do, we've got a point, we've got a line, we've got an angle. Now all we have to do is create a set of these things. So we imagine that if this sphere, we just make the rule that this sphere is always going to be covered so that it's packed with other spheres, then the total set of points inside looking out will be the set of all the contacts. So the simplest way to do that is this. Okay, so inside of this sphere, it'll have a center and 4 points, and they'll be equally spaced because these second spheres are all the same size. Okay, so we go from point to line to angle to set. So we really only have 4 things we need to worry about: point, line, angle, set. And in the process, we create this idea of dimension or size scaling. Okay, but it's related because the number of spheres that you can put around this is related to the size of the spheres and the relative size of the spheres. Okay, well, there's an infinite number of ways that this sphere can be coated with other spheres, but there are some ways that are more perfect than others. When these spheres on the outside are all the same size and they all perfectly fit together, then that would be the simplest possible way, the least amount of entropy. Okay, so if what we want to do is create this, then we just do this. We call this 1 and we call this 2, and then we ask the universe how many spheres does it take to coat one with two? And the answer is 20. Well, this simple algorithm of packing one sphere around another generates a dodecahedron. Well, we already know that if we have this set of points, then we have this set of points, and we have this set of points. Okay, so if we have this one, we have this one and this one. And if we have this one, we can get this one, because all we need to do is take a ball and put it in the middle of all these others. So if we already have the information here, then we already have the information here. This one is derived from this one. Okay, so in fact, the spatial information needed to create a dodecahedron is the relative size of these two spheres, which is just two lines, the ratio between this line and this line. If I know that ratio, I have all the spatial information I need to generate not just the dodecahedron, but all 5 perfect solids. So this ratio is a universal geometric ratio that generates perfect symmetry. Well, it's kind of like pi. I mean, it's the universal ratio of radius to circumference. The difference is it's digital. Okay, pi is not digital because it's transcendental. Well, this is transcendental too, because if you look at if you look at these 8 points that are on this, then there's 12 points. These are Cartesian, but then there's 12 points that come in sets of 2s. The blue ones are not, the yellow ones are not, and the red ones are not. So there's these 12 points that are not digital. They depend on phi, which is a transcendental number. It's the golden ratio. So that's why I call this phi-ometry, because we not only use phi, but we generate it digitally. This is a digitization of phi. Well, it's also a digitization of pi, because pi is just this concept All right, we already saw that we have a radius, which is a line that generates another line. Well, when we take the line that's the circumference and the line that's the radius, there's no set of digits that will divide this one into that one. Okay, but this is just a contrivance. It's contrived on a plane. When we go up to a sphere, if we break it down to just 4 lines and 4 points on a sphere, okay, then all we're doing is contriving a system of notation that says this is plus and this is minus, this is plus and this is minus. Well, this creates a problem with square roots, because our convention is that you can't have a negative times a negative is a positive. So if this is 1 and this is -1, then this is a positive number, and this number can't exist, so it's imaginary. So we contrive this imaginary number. Well, this is no more unnatural than -1. It's just contrivance, because we can start rotating these things around, and we can see that that it's just a system of notation that's causing it to contrive. So then what they do is once they create this contrivance, then they create what's called the complex plane, which is just this, okay, which is just this cross, but we now have, we move I up into the positive y-axis, and then we start doing stuff with that. It's very powerful, but it's also entirely contrived, and so is pi. I mean, we can see what this is we've just broken a circle down to 4 points, and we know that that's a square. Well, that's a square on a plane, but on a sphere, it's a tetrahedron. Okay, the 4 equally spaced points on a plane, which we call a a we call a square. In space, it's a tetrahedron. So all we have to imagine is that these points, these 4 points, move to equally space out. So a square in real space is actually a tetrahedron, which is this. Well, if this is going to be pi, well, if the points connecting, well, first of all, if this is going to be the complex plane, why is this not the complex plane? Why don't we treat this as the complex plane and put it into all dimensions instead of contriving it to be in 2 dimensions? This is a better complex plane than this. But now we can start to see that the pi, depending on your definition of how much symmetry you're going to break. I mean, when we break it with 4 points, we get this. Okay. Well, when we break it with 20 points, we get this. Well, the length of going around the sphere with 4 points is shorter than the length of going around the sphere with 20 points. So why not define pi by these lengths, and then they'll be digital. So we can have different flavors of pi. We can have tetrahedral pi, we can have dodecahedral, we can have cubic pi. I mean, we can, pi can now be, it could get out of the plane. And more importantly, we can have phi, which we'll talk about scaling and fractals in the next video, but we can create a universal scale factor. This is based on the ratio of two numbers, 2 lines, and it can just multiply our math from little to big and from big to little, which is what we want to do. So if we just start with the premise that we have 2 spheres, we can generate this. Well, if we generate that, then we also generate this, and we generate this. This is a subset of this. This is a subset of this. Well, these are all supposed to be white balls because by coloring them, we're breaking the symmetry further, and we're creating more information, which is what we want to do in biomath. So, we can now imagine a kind of mathematics that's based on individual spheres, where if we were to put a bunch of random spheres into a box and start shaking them, we know that eventually they will create the 5 perfect solids. The solids will emerge out of this random chaos. They will emerge as the lowest entropy form. So this is what the universe is trying to create. So we can see that if we call this outer sphere 1 and we call this inner sphere 2, then we need 5. We need at least one this small and at least one this big. And so, and between the small one and this big one is this outer one. We could reverse it and keep the middle one the same. Then we could create 5 other digits. So 1 is not the same size as 2, and 2 is not the same size as 3. But we can create this infinite set of digits, which are different spherical volumes. And then these volumes can tell us what their lengths are based on how they're calculated by the universe. So now we can have this completely random, chaotic universe that possible lengths randomly range from the smallest to the largest. And the machine, the universe, with each clock tick, what it's doing is it's calculating the lowest entropy state for each. I just heard the camera click off, so I better wrap this up. So what we're trying to imagine now is a universal machine. The only thing it does is generate spatial coordinates. But by virtue of generating these coordinates, taking randomness and organizing it using natural selection or any kind of selection, it's generating the reality that we perceive, and that reality is emerging out of this process, this spatial process of calculation. So we're gonna flip causality. We're gonna say, look, we're not going to tell the universe what geometry it is. We're going to ask God, the source of all knowledge, what geometry are you creating? And then we're going to try and understand that, because we want to use that as a basis of understanding the molecules of life. This is what they're doing. They're generating their own coordinates. So it must be a manifestation of some logic that they inherit. So the universe generates this logic. The atoms inherit it. The atoms use it to generate life. And then it goes up the chain of causality. We inherit it. That's what our intelligence is. Okay? There's this fundamental intelligence at the basement of the universe, compounded over 15 billion years. And eventually, after playing this game, it took 15 billion years to create my brain. But now I've inherited all of these intelligences that are mathematical. They came from the universe itself. This is a fundamental property of the universe. This is the game that we're trying to play. This is what science is trying to do. It's trying to define just this kind of logic. So that's why this kind of simple-minded thinking is actually, it's easier because there's fewer parts. There's less complication. It's less to keep straight. We're not creating order from order. We're creating order from chaos. That's what life does. The atoms are behaving chaotically, and life orders them. So in the next video, I'm going to describe the single most powerful concept in geometry, which we haven't even discussed yet, but we'll do that later.